Sci-fi stories often center their magical technologies around extremely rare or invented materials to explain their wondrous properties. From the kyber crystals in lightsabers and dilithium for Star Trek warp drives to unobtainium and hard light projectors, science fiction often turns to impossible means to explain their impossible effects. But what kind of magical materials actually exist, and how could humanity benefit from their uses? And just how expensive would procuring or creating these materials be? Welcome back to Sirius Science, and these are 5 rare materials humanity could use to make the future all the more wondrous. Let's start by laying down some framework. The rarity of a material can come from multiple different factors. The simplest is scarcity, or how difficult it would be to find something in the wild. Some examples would be gold or osmium, as they are exceptionally rare, but both are used extensively in the modern day for a wide variety of applications. Another factor is the workload required to create something. Antimatter exists all throughout the universe in vast abundance, but takes billions of dollars and many years of constant production to create even the tiniest amount of it here on Earth. Another simpler example would be saffron, an extremely expensive spice due to the fact that entire fields of crops only produce a few pounds of the substance for a year of growth. One of the more interesting factors of determining a substance's rarity is how long that substance will exist. Humanity has artificially created elements that we can safely say exist nowhere else in the universe other than Earth, as those highly unstable elements decay in fractions of seconds and take monumental amounts of energy and equipment to produce. Even plutonium, one of the more useful nuclear fuels, is only produced naturally in extremely small amounts, and every ounce of the metal that we use today was created by us. But I want to look a bit farther, more on the grand scale of the universe. While gold may be rare here, there are entire asteroids packed to the brim with the metal, and uncountable amounts of similar concentrations exist all throughout the universe. Compared to the rest of creation, wood harvested from trees could buy entire star systems, as it exists only in one place, on one planet, Earth. So what overall are the rarest materials in existence, and how do we or could we use them to bring the future just a bit closer? Just as an aside, I will be ignoring the more well-known materials such as antimatter or platinum, as their scarcity can be more easily understood. More so the materials that exhibit incredible properties that would aid in technological use, and I will explain their uses as we go. Let's start with a material built from some of the most abundant elements in nature, but formed into a truly alien shape. Carbon is the best currently known element for the formation of life, as everything about their atoms promotes stability and strength. Carbon binds to iron and creates steel, reinforces extremely long and advanced protein chains needed for complex life forms, and bonds with one another in highly durable shapes. Graphene, one of the strongest and most expensive of materials, is only 1 atom thick, but is 200 times stronger than steel. While graphene isn't the material I will be discussing, this one is made up of the same stuff, but wrapped into a highly durable sphere. Endohedral fullerenes are essentially about 60 carbon atoms arranged in a soccer ball-like shape, but contain a single atom of a different element within their sphere. These shapes are entirely artificial and produced using specialized equipment that form these complex shapes, then blast another element into their centers for containment. These materials are so difficult to create and control that an ounce of them would run you about $4.2 billion to purchase. But the incredible part of this material is that you would only need a single fullerene to accomplish what they were designed for. Our modern day is focused on precision, as to pinpoint your location or create something with necessarily tight tolerances requires extremely fine dimensions. One of the difficulties in exact geopositioning is timekeeping. How your GPS knows where it is has to do more with time than location. Satellites ping GPS systems by telling them where they are and how quickly their messages reach the device. They do so using electromagnetic radiation, aka light waves, which move just about as fast as you can in this universe. The difference between knowing where you are within a few feet to a few miles depends on fractions of milliseconds of measured time. The most precise clocks on Earth are massive room-sized machines that capture and monitor elements such as cesium or hydrogen. Hydrogen atoms are too small to contain and would slip through these endohedral fullerenes, but cesium would be unable to escape its carbon cage. The reason atomic clocks are so large is that it takes a lot of containment and electricity to monitor a single atom of cesium, where fullerene clocks would already contain that atom by design, as well as require far less energy to monitor, and could reach sizes that could easily fit within small devices like phones and watches. This precisely confined atom could be measured against satellite signals and provide location accuracy within a single millimeter. This technology also offers impressive benefits for medicine. We can scan the human body fairly accurately today, but there is still a lot of room for improvement as we regularly use toxic dyes and chemicals in order to reflect our scanning frequencies from within a body. These chemicals are administered in small amounts and give hazy images due to the amount needed for a clear scan often being enough to kill that human. However, if these dye molecules were held within fullerenes, they would be isolated from the human body and could not be absorbed as they passed through the bloodstream, allowing for clear and safe scans that could detect damages and cancers far easier than what we can do today. These nanoscopic structures could also play a major role in other applications that require the isolation and monitoring of a single atomic element or molecule. There really isn't anything more precise than a tool with a tip made up of only a handful of atoms, and its usability skyrockets if it contains a single atom of a specific element. Atomic decay could be precisely mapped. Specified elements could act as unreproducible tokens for security systems held within spaces that could be easily read. Isolated substances could be administered both medicinally and industrially into systems that would react poorly to their external application, and the ultra-precise measurement of reactionary particles, atomic collisions, and particle detection substances would be far easier to remove from the influence of the outside world. Fullerenes, also known to most as buckyballs, do occur in nature, albeit rarely, but these isolated elements trapped within are thought to only exist within humanity's laboratories, and are therefore quite expensive in both their rarity and difficulty in manufacturing. There is, however, another ultra-rare material that we already know of, one with impressive thermal properties. Rhenium is the 6th rarest metal found naturally occurring within Earth's crust, with a scarcity of about 0.4 parts per billion. While you may be wondering what the 6th rarest metal on Earth is doing as the second entry on this list, it has some truly incredible properties, one we have only now begun to explore. It may also surprise you to know that it is already used in aerospace and electrical applications. When mixed with other durable elements like nickel, it creates something not seen in nature, a metal that can be heated to extremely high temperatures, like 5,800 degrees Fahrenheit or 3,200 degrees Celsius kinds of temperatures, and it resists expansion as well as wear. Every metal we use in our machines is susceptible to heating expansion as well as heat-induced cracking. This means that when we run our technology hot, for example within rocket nozzles or high-energy electrical connections, those metals quickly degrade and require replacement. This metal could be alloyed with many different elements, creating new and uniquely useful high-stress components. Rhenium nickel is used today in just that, rocket nozzles and electrical connections that need to relay a large amount of power quickly. But we have only known of these kinds of alloys for about 60 years, leaving quite a bit of room for future discoveries. Electrical applications could come in the form of high-powered capacitors capable of discharging city-scale levels of electricity without melting its components, as well as run durable and high-tolerance connections for far longer than their modern equivalents. Uses for such powerfully heat-resistant metals could be seen in one of the most interesting of possible discoveries: how the cores of stars function. While stars can exist within ranges of 4,000 to 90,000 degrees Fahrenheit, we could explore the depths of cooler ones to examine the process of stellar fusion up close, as well as the surfaces of punishing worlds. Machines could be clad in rhenium and sent to collect molten samples from some of the most dangerous places in our solar system. Crewed missions to the surfaces of Venus, Io, and Mercury could be landed successfully, albeit perhaps needing some equally innovative advancements in thermal radiation to keep anything within them cool and alive. While places like Jupiter's core are far hotter than our own star, we could send probes to scan the depths of other gas and ice giants. Our attempts at reaching some of the most extreme environments of the universe may have gotten just a bit closer. Like subscribing to this channel may bring quite a bit of new science and ideas to your life. Yep, still doing it. While we are on the subject of a naturally occurring substance that shows promising features for the future, let us move on to the third entry, that being tritium. Tritium is created by adding 2 protons to hydrogen atoms, and is only naturally produced in extremely small quantities in our atmosphere by cosmic rays energizing atomic hydrogen. Not only does this substance occur extremely rarely, but can only do so on worlds with hydrogen in their atmosphere, eliminating many other worlds in the universe as possible sources. Most, if not all, of the tritium tritium we use today comes from artificial nuclear fission. While the specific conditions to create tritium may be rare, it can be easily created in nuclear reactions from the most abundant element in the universe, but must be done so using expensive and dangerous machinery, causing its price to skyrocket to $30,000 per gram, almost as costly as natural diamonds. Tritium has begun to see a more dedicated use in nuclear science, as it gives off beta radiation that is slow-moving but energetic, strong enough to energize other atoms but weak enough for human skin to deflect it, making it perfect for jump-starting nuclear reactors as well as fusion bombs. Its most common use is in long-lasting phosphorescent applications such as weapon sights, clock faces, and even miniature photovoltaic generators when wrapped with solar paneling. I actually own a keychain that contains tritium, one which I purchased almost 7 years ago, and I can attest that it is still glowing strong to this day. Tritium itself does not glow, only emit energetic particles, and it must be paired or encased within a phosphorescent paint that turns those energetic particles into released light. Tritium has a half-life of about 12 years, so it won't act as a reliable source of lighting for extra long durations, but it does offer more by way of nuclear physics than it does for visual appeal. Tritium can be made from the most common element of all, using other active nuclear reactions to form, and can act as nuclear fuel source itself for producing reactions. Plus, it decays into another extremely rare and highly sought-after nuclear fusion material, helium-3, essentially being two rare and useful materials at once. Helium-3 is one of the most promising fusion fuels we know of, but is extremely rare, only being produced as a byproduct of maintaining our nuclear arsenals, all of which produce about 15 kilograms of the substance every year, making it entirely artificial on our world. It is, however, produced naturally in extreme exoterrestrial environments, one of which being the surface of our own moon, and is one of the primary defenses for the installation and activation of lunar mining infrastructure. If helium-3 is rare enough to try to go to our own moon to collect, then it being created as the product of tritium reactions may offer a cheaper and closer to home method of collection. Tritium may already be in use today, but those uses leave a lot of room for improvement. While tritium photovoltaic cells are outperformed by radioisotope generators, tritium would offer powerless lighting for situations where energy demands are tight, as well as energizing collective fission materials for the transmutation into heavier, more useful elements. This next item on our list will be a bit different, as it technically encompasses a vast swath of different substances. These substances are extremely rare, but have the opposite problem compared to most other ultra-scarce materials, as they only exist here on Earth and are entirely man-made. Metamaterials. I've done a relatively comprehensive video discussing the specifics of metamaterials, which you can watch here, but I will still go into some detail as well as explain how they can and are changing the future to look more like our sci-fi ideals. Essentially, a metamaterial is two or more elements or substances mixed together, usually in a crystalline pattern of uniform arrangement. The fantastical property of metamaterials comes about when two substances are mixed together without losing the material properties of either, and sometimes creating entirely new effects through their combination. Metamaterial science is currently dominated by how materials affect electromagnetic radiation, as the control or deflection of light, from radio to gamma, provide many extremely useful properties, particularly in precision optics and even prospected visible and infrared cloaking technology. They also offer spectacular electronic potential, as we have been able to mix certain elements that show high levels of conductivity to research room temperature superconductors, which would bring about absolutely incredible advancements in clean battery technology, lossless power transmission, and extremely versatile capacitors. I've actually also done a video explaining how superconductors work and what they could mean for the far future of humanity, which can be found here. But I'd like to officially submit one particular metamaterial for this list, as it is rare, expensive to manufacture, and is a relatively new invention. Nanometer perovskite. Perovskite is a naturally occurring crystalline structure, usually formed by titanium and calcium, that forms an extremely strong cubic lattice. The rarity of this naturally occurring crystal comes when we create two-dimensional sheets from them, essentially graphene but made up of different elements. These perovskite crystal sheets offer an incredible boon to photovoltaics, as when photons strike their structures, it conveys electricity along the material. Modern solar cells run at about a 15 to 20% efficiency, converting converting 20% of all the light that falls on them into electricity. But these metamaterial cells can do so with an average of 30%, even seeing 47% efficiencies within modern testing labs. These new solar panels would be formed from common materials and run at double the efficiency of modern cells, eliminating much of the toxic waste metals usually associated with solar cell recycling. They may not be as expensive as some of the other things on this list, but are rare in that they are just now seeing use in our power equipment, having been only discovered about 14 years ago. This material could revolutionize clean energy, both in its efficiency and in their disposal. They could also see wide use in broadband wavelength scanning, as modern antennas are only able to pick up on a short range of electromagnetic wavelengths. This material, however, can receive energy from anywhere between visible light and infrared, a wide section of the light spectrum, allowing for a diverse range of possible collectible light over other narrower materials. And before we move on to the final entry, I'd like to point out some runner-ups that didn't make the cut, either by being already well known or having properties that wouldn't really benefit humanity on a large scale. The most obvious answer is antimatter, of course, but others are more interesting, such as astatine, the single rarest element on Earth, with there being approximately only a single gram of it in the entirety of our planet. Another honorable mention is a crystal called chiathuite, a crystal so rare that we have only ever discovered a single stone of it as recent as 2010. The last item on our list has often been described rather poetically in the materials I have been able to find and read, as a sort of godsend from outer space, as it does not occur naturally here on Earth. Almost every single electronic device we produce requires magnets or electromagnets for some function, whether that be neodymium or samarium for speakers, apertures, and resonance imaging, as these kinds of rare earth magnets are desirable for their magnetic permanence, or in other words, their near eternal and unchanging magnetic fields. These kinds of rare metals are extensively and painstakingly mined all across the globe to keep up with our technological demand, creating dangerous and lasting effects on the surrounding environments. But about 40 years ago, something was discovered, a seemingly alien metal with equally mystical properties that had fallen from the stars in meteorites, one that had magnetic permanence but was made of some of the most common metals in all creation. Tetratenite is an alloy made up of nickel and iron, but forms under extremely time-intensive processes. Essentially, as meteors are formed from molten metals, nickel and iron are mixed together and begin cooling. Normally, molten iron will arrange its atoms in relatively uniform directions, creating natural magnets, but if the metal is cooled too rapidly, these atoms will not have as much time to line up and create stronger magnets. These magnets also have the property of high coercitivity, or in other words, it resists the deformation of its own magnetic field under the influence of surrounding stronger fields, meaning it will continue to function in messy electromagnetic environments. Tetratenite, however, is such a strong magnet because it takes a very long time to cool, as in losing single degrees of heat over millions of years, allowing vast amounts of time for atomic reconfiguration, creating some of the most powerful and permanent magnets we know of. As a matter of fact, I couldn't even find much by way of pricing for this material, as it is a new discovery, exceptionally rare and highly sought after. As far as my research could tell, this material is truly priceless. However, humanity has begun a process it regularly employs, that being our belligerence at the universe for not providing enough of what we need, requiring us to create it ourselves in laboratories. Recent breakthroughs in material science have made it possible to create these magnets artificially, but this is still a brand new advancement, and has not seen much use in manufacturing. Almost every single machine that turns electricity into mechanical motion uses magnets to do so, while larger and more robust machinery requires magnets strong enough to keep their fields while operating under intense pressures and temperatures. This is where we usually turn to rare earth metals, as these reinforce our magnets against these forces, but these new tetratenite magnets would be able to accomplish the same tasks without needing extensive mining and destruction to acquire. With these new magnets, humanity could accomplish some truly incredible feats, but probably not the ones you're thinking of, especially if you are used to the kind of content I make on this channel talking about FTL ships and structures the size of planets. These could instead reduce the harmful effects we inflict on our planet and its ecosystems by eliminating the need for damaging and costly mining sites. As we have moved through time, we have used our ever-expanding knowledge bases to better the lives of everyone who lives moving forward, whether that has led to unforeseen consequences or wild successes. We constantly develop our world towards better, cleaner futures, and it may come to pass that something we thought of as a desirable alternative may be more destructive than their older counterparts. For example, the creation and recycling of electric car batteries being far more harmful than the emissions of fuel-burning cars. These setbacks should not be seen as failures, but learning pains of figuring out how our universe works and how to best survive within it. We learn more after a misstep than we do automatic successes, and the road to technological growth has been plagued by both for as long as we have been starting fires in the wilderness. As we move forwards, it is important to remember that as long as we pick ourselves back up from our stumbles, we will have to come out of those trials stronger and smarter, ready to create truly wonderful futures for our children and their own. Who knows what kind of magical materials humanity will invent while under the pressures of lesser methods, and even more nebulous are how those inventions will change the world, whether or not they stumble or stride. Thank you all so much for watching, and don't forget to stop by the community tab of this channel where you can vote on the next topic for the next video.